if we have a compound with an acidic alpha hydrogen, okay, so anything that can form an enolate, we can use LDA. The last two we talked about were specifically beta diketo compounds, or beta dicarbonyl, I suppose. We should really be able to do it with almost any carbonyl compound that has alpha hydrogens. We do, however, have to use LDA. The weaker ethoxide or whatever, the weaker bases like those can only really be used with the beta dicarbonyl compounds. So we'll use LDA to fully form an enolate from other carbonyl compounds, and then we'll alkylate it with a methyl or primary alkyl halide. So it should be very simple. We cannot do this with aldehydes. Aldehydes, the carbonyl is so electrophilic that any enolate we form will just instantly attack a carbonyl of the next molecule. So that's in the next chapter in our condensation reactions. So aldehydes are excluded from alkylations, essentially, but we can do it with most anything else, right? Here's some esters and lactones. In our lactone, this is butyrolactone because it came from a 4-carbon carboxylic acid, essentially, and we make a 5-membered ring with an O in it. That's the ester. Okay. So it has alpha hydrogens. LDA will remove an alpha hydrogen. Leaving one behind, which then I can alkylate. Right? Let's just use something simple like methyl iodide. Okay. So, very simple. Here's an ester. This is ethyl 2-methylpropanoate. Right? Essentially C double bond O OET, CH, and then 2 methyl groups attached to the alpha carbon already. But since there is an alpha hydrogen, LDA can remove that. We end up with this compound, right? The alpha enolate there. Alkylation with something like methyl iodide will give us a 3rd methyl group on the alpha carbon. Okay. If I have just a regular old ketone, this is 2-methylcyclohexanone. LDA will deprotonate, but remember LDA is so bulky, it's going to choose the more available, the less hindered alpha hydrogen. Okay? If we were trying to do this under acidic conditions, we could have gotten the more hindered one, but if we do the less hindered alpha hydrogen, the methyl over there stays the same, but we end up with something like that. An alpha enolate on the less hindered position, which can be alkylated. And that gives us a symmetrical compound. Okay. 2,6-dimethyl cyclohexanone. Okay. So doing it with LDA, we can alkylate at the less hindered position. We're not going to end up with 2 at the same position unless there's only one type of alpha hydrogen to remove. Now, interestingly enough, nitriles also have alpha carbons, right? If I have C triple bond N, that behaves much in the same way as a carbonyl. So the carbon next to the nitrile has, in this case, this is phenylacetonitrile. It has hydrogens attached right there. So exact same thing will happen. Phenyl group, CH, but now with only one hydrogen next to the nitrile. Okay. So that essentially makes an enolate-like ion. So again, with an electrophile like methyl iodide, will allow us to alkylate alpha to a nitrile. So CHCN. Just like that. So if it's a compound that has only one carbonyl to it, we need to use LDA. We can alkylate, and that gives us a variety of lots of different interesting things that can happen. This, of course, is not compatible with carboxylic acids, right? Because C-double-bond-OH. Because if we reacted that with LDA, we would just instantly deprotonate the carboxylic acid and get a carboxylate. So if I want carboxylic acid that's alkylated, we have to go back to the malonic ester synthesis that we did before. The best way to get a methyl ketone is the acetoacetic synthesis. Anything else, we'll take our chances with direct alkylation with LDA. It's best to use a gentler base whenever possible because that's going to be the most compatible with other functional groups in our molecule. But if we have a relatively simple molecule that has preferably only one type of alpha hydrogen to it, we can very cleanly deprotonate with LDA, and in a second step add the electrophile to have a direct alkylation.